All right, everybody, let's talk about more statistics. So let's talk about central tendency a little bit more. So first of all, some learning outcomes we have here. We will understand the purpose of measuring central tendency, define and compute three measures of central tendency, describe how the mean is affected when a set of scores is modified, describe the circumstances in which each of the three measures of central tendency are appropriate to use, explain how the three measures of central tendency are related to each other in symmetrical and skewed distributions, and draw and interpret graphs displaying several means or medians representing different treatment conditions or groups. So you want to be familiar with summation notation and frequency distributions, chapter 1 and 2. So central tendency, that is a statistical measure. The idea is that it's a single score that defines the center of a distribution. The purpose is to find what's most representative of the group. You have your mean, your median, and your mode. So this shows what distributions might look like in terms of where the data might be dispersed. So there's no single best concept of central tendency. Again, it's mean, median, and mode. So we have our population mean. This is our formula. Our mean is the sum of X, or the values, divided by the number of all the scores, or the N, or the population. The sample mean is the sum of all the values over N, or the sample amount. So really everything divided by the number of participants, people, your group, that sort of thing. Some alternative definitions for the mean: dividing the total equally, the sum of the scores equally divided by the number of scores, the amount each individual gets when the total is divided equally among individuals, the mean as a balance point. The value of the mean will always be located somewhere between the highest score and the lowest score. And there's absolutely applicability in this if you're working on your infographics. Try to negotiate the mean with your salary in your future job. Maybe you've been out looking at salary.com. So this is a way to look at the mean. It's a balance point. It's the average. A mean is an average. Then we have the weighted mean, and that's when we have two different groups that we're trying to compare with each other. That's what that's for. So you want to determine the combined sum of all the scores, determine the combined number of scores, and divide by the number of scores by the total number of scores. The sum of the X values for each one is the mean divided by N1 plus N2. It makes it a better average, basically. That's your weighted mean. This is what the frequency distribution table looks like for your mean. So a sample of N equals 12. Again, that's your sample amount. Has a mean of 8. What is the value of the sum for the sample? So think about that. And of course, our answer here is 96. So changing the value of any score changes the mean. Introducing a new score or removing the score changes the mean. Unless the score is added or removed, it's exactly equal to the mean. Adding and subtracting a constant from each score changes the mean by the same constant. Multiplying or dividing each score by a constant multiplies or divides the mean by that constant. Another way to illustrate the concept of the mean is to really just look at if you recompute the mean. We'll work on that with some worksheets here. So again, it's sensitive to changes in scores, again, sort of the balance point. So learning check 2, a sample of N equals 7. Scores is M equals 5 for the mean. All of the scores doubled. What is the new mean? So what do you think? And our mean is 10. Then we have the median. The median is like the midpoint right in the center. So if you have 7 numbers, the median will be the fourth number right smack dab in the middle. That's where 50% of the scores are distributed or located. So that's how you can remember the median. So locating the median, put the scores in order, lowest to highest, identify the middle score to find the median. The middle score is 8, so the median is 8. As you can see with this example, this is an example of 5. Median is right in the middle. So if you put the scores in order, lowest to highest, locate the median by finding the average of the middle 2 scores. So 4.5 is exactly half the distance between 4 and 5 on the interval for the ratio score. So the middle 2 scores are 4 and 5, so the median is 4.5. So you put the scores in highest to lowest, you find the two middle scores. Remember, we're talking about distance here from the median. So finding the precise median for a continuous variable. A continuous variable can be infinitely divided. The precise median is located in the interval defined by the real limits of the value. We must determine the fraction of the interval needed to divide the distribution exactly in half. The fraction is equal to the number exceeded to reach 50%, the number in the interval. This process is called interpolation and can also be used to estimate an intermediate value between any two other x values. So it's a fraction divided by the number needed to reach 50%. For your numerator, divided by the number in the interval. So for example, with 8 scores, the median should have 4 scores below and 4 scores above it. The scores fall below the upper real limit of 3.5 is what it's showing here. So again, it's really half. I feel like there's a lot of ways to think about it. So then we have, so the mean's a balance point. That's like your average. The median's the midpoint. The median is defined by the number of scores. So again, median right in the center, to the left and right of it, same number of scores. Mean, average. We'll talk about the mode in a minute here. So, and the mode, which I'll tell you about in just a moment, it's a number, you can have unimodal or multimodal. And that's the number that occurs the most frequently, or the numbers that occur the most frequently are what the mode is. So again, if you notice, the mean does not necessarily divide the scores into 2 equal groups. In this example, 5 of the 6 scores have values less than the mean. Again, the mean's the average. So what do you think? True or false? It is possible for more than 50% of the scores in the distribution to have values above the mean. True or false? It is possible for more than 50% of the scores to have values below the mean. So true, more than 50% of the scores in a negatively skewed distribution will be above the mean. False, the median is defined as a score that divides the distribution exactly in half, 50% above and below. And this was, yeah, median. I think I read mean. I had to say median for that one. Okay, so the mode, again, that's the number that occurs the most. So you can be multimodal, which means you have more than one mode, or unimodal. Whatever number is repeated or the most frequently occurring, that's your mode. This is an example of a bimodal distribution where we have more than one mode. 17 and 22, I believe, occur about the same, maybe? Well, similar. But ideally, a mode is when the same number occurs. So let's say, yeah, maybe that 18 right here, 18 and 23. It's like that occurs the same amount of times. Like I said, it's whatever are the most. So I really think this one should be 17 and 22. Multimodal, in the best sense, is defined as an equal number of scores that occur the most. So symmetrical distributions, mean and median, have the same value. If there's exactly one mode, it has the same value as the mean and the median. Thus, in a perfectly symmetrical distribution with one mode, all 3 measures of central tendency, the mean, median, and mode, have the same value. A distribution may have more than one mode or no mode at all. Here are some symmetrical distribution examples. You have the mean, the median, the mode, the median, and the mode, and no mode. So we have normal right here, bimodal, and rectangular for our symmetrical distributions. So skewed distributions, that's when it's going to go to the left or the right because of how the central tendency is going to pull on it, which is your mean, your median, and your mode. So your mean influenced by extreme scores, outliers that can affect it, positive or negative. Median, in order to divide scores in half, is found towards the long tail, but not as far as the mean. The mode is found near the short tail. If the mean minus the median is greater than 0, the distribution is positively skewed. If the mean minus the median is less than 0, the distribution is negatively skewed. What does that mean? Here it is graphically for you. This is positively skewed with your mode, median, and mean, and this is negatively skewed with your mean, median, and mode. So the distribution of scores shows the mean is equal to 31 and the median is equal to 43. This distribution is probably positively skewed, negatively skewed, bimodal, or open-ended. So take a moment, pause me, think about it, and that is negatively skewed. So the next thing we want to talk about is what measure of tendency we should use. So appropriate to choose a mean if you can calculate the sum of the values. This is the sum of, or the Greek sigma. X is always the values. You know the value of every score. Could be misleading with extreme scores, outliers, skew distribution. The mean's the best with a normal distribution. An ordinal scale, a nominal scale, open-ended distribution could all throw the mean off and then it could be misleading. Median, you want to use if you have extreme scores, remember that's in the middle, a skew distribution, undetermined values, open-ended distribution, ordinal scale or nominal scale. Nominal scales, discrete variables describing its shape is when you use the mode, and interval or ratio data except to accompany the mean or median could throw you off in the mode. And with the median, a nominal scale. Remember, nominal scale is like an adjective. It's like qualitative. It's telling a story. So this is a frequency distribution with one extreme score. If you notice, the graph shows two breaks in the x-axis. Rather than listing all the scores from 0 to 100, the graph jumps directly to the first score, which is x equals 10, then jumps directly from x equals 15 to x equals 100. The breaks in the x-axis are the conventional way of notifying you that some values have been omitted. So this is a line graph with means. This is the relationship between independent variable drug dose and dependent variable food consumption. Because drug dose is a continuous variable measured on a ratio scale, a line graph is used to show the relationship. So here we go. This is median weekly income in US dollars for different types of teaching positions. So let's do some more learning checks. Decide if each of the following statements is true or false. The mean uses all of the scores in the data, so it is the best measure of central tendency for skewed data. If the mean and the median have the same values, the distribution is probably symmetrical. Think about that. And false, the mean will be moved towards the long tail in skewed data, so it may not be representative at all of the middle. And true, when the mean and the median are the same, the distribution has to be symmetrical, balanced to the mean about 50% above or below. And if you have questions, you should email me or call me. I think you all have my phone number and my email address. It's jkmack@ferrum.edu, or you can call me at 786-879-01. I'm sorry, 786-879-0179. Sorry, it changed recently. So we'll pause that and we'll do either some more lecture in a moment or explain some homework. So explaining some more stuff to you momentarily. All right, everybody, let's talk about chapter 4 a little bit. And all the homework assigned so far, you should have already done. What I was trying to say before, and you should probably talk to me about when you would like to have class, was that for those people that weren't able to get the book or something, I was going to give you your percentage of your in-class assignments against the SEND gauge is what I was talking about. But hopefully I'll hear from some or all of you on in-class lectures, because I think you get a lot more out of this. You can ask me questions. We can do office hours. I can explain stuff. The first few chapters are pretty straightforward. It gets more involved as we get into things like probability, F-scores, some of the squares. It does start to get more involved after this chapter. Anyways, let's go ahead and talk about variability. So variability has to do with how scores vary. So when you think about it, think about the clumping of scores. So our learning outcomes for today, in addition to what I just lectured about, would be to understand the purpose of measuring variability, define the range, compute the range, and chapter and the assignment 3 and 4, and there is a recorded video from me walking you through that assignment in detail, would also help with that. You want to understand variance and standard deviation, calculate the sum of the squares. It's really not that big a deal. I'll show you the sum of the squares in a moment. Variance and standard deviation of population, calculate the sum of the squares, variance, and standard deviation of the sample. And let's do actually a brief pause because I feel like the sum of the squares really confuses folks sometimes. So if we grab an Excel sheet here. All right, let's talk about what the sum of the squares are, all right? Okay, I think this is something really hard for folks to always comprehend. Let's do another screen share. All right, here we go. Sum of the squares, I'm gonna refer to that. All right, so we're gonna say X or values. In fact, we'll zoom in, okay? Zoom in a little bit. Zoom in a little bit. So we have our X values, okay? And let's just come up with some values. So just random numbers, okay? Let's look at that. These are different. Okay, those are some values, all right? Pretty easy, pretty straightforward. So if we want our mean, all we would do is we would take these and we would sum them. That's our sum. How many values do we have? Well, we have 1, 2, we have all the way to, we got 11 values. So we just take this and we divide that by 11. That's your mean right there, okay? And your mean is yours, and your standard deviation is your, well, we'll come back to that. So anyways, these are our X values, okay? So now we're going to square the values. We're going to square these, okay? So I'm just going to take this number and I'm going to make it to the second power. So like that. Okay, 3 times 3 is 9. Pretty straightforward. We're going to square all of these. Okay, those have all been squared. This number times itself squared. So what the heck is the sum of the squares? Well, we have them all squared. We're just going to sum them. That is your sum of the squares, or think about it as the squared values. Literally that easy. That's going to come up a lot. You're going to want to know how to take your values, square them, and calculate the sum of the squares, which is literally squaring the values and summing them together. So let's go back to our lecture here. Zoom, please tell me a good time to meet. I think you would all enjoy this a lot more if you had regular class times and you could ask questions. So please get back to me, everybody, on what you think on that. So we'll define range, calculate some of the squares, variance, standard deviation of the population, some of the squares, variance, standard deviation of the sample. Summation notation, central tendency, mean, and median. So variability, you can think about it as distance. A quantitative distance measure based on differences between scores. That describes the distance of the spread of scores or the distance of a score from the mean. Purposes of measure of variability: describe its distribution, clustered or spread out. Measures how well an individual score represents the distribution. So this is just some population distributions: adults height in inches and adults weight in pounds. So some measures of variability: you have your range, your interquartile range, your variance, and your standard deviation. Your range is the distance between the numbers. So if we have the numbers 1 through 10, it's 10 minus 1, your range is 9. The real range is 0.5 above and below, and you basically add 1 to it. So the real range of 1 through 10 would be 0.5 to 10.5, or it would be basically 10, because it's 9 when it's the range. The interquartile range, we'll talk about that. We'll talk about variance and standard deviation. And variance, once you know the variance, you just take the square root of that to get the standard deviation. Literally that straightforward. So the distance covered by the scores and the distribution from the smallest to the largest score. For continuous variables, the real limits are used. The range, the URL is the upper real limit, the LRL is the lower real limit. The range more accurately defines the maximum score minus the minimum score, the large number minus the small number. Again, the real range has +1, and there's absolutely a video entitled Assignments 3 and 4 Explanation that walks you through that in greater detail from me. So that's based on 2 scores. Not all scores are represented, an imprecise, unreliable measure of variability. So we have the interquartile range. Quartiles are percentile ranks. You have 25, 50%, 75, and 100%. These are called the first, second, thirds, and fourth quartiles, respectively. And they divide the distribution into 4 equal parts that each corresponds to 25% of the distribution. The interquartile range, or IQR, is the distance between the X values that correspond to the first quarter 1 and the third quartiles quarter 3. Scores fall in the middle 50% of the distribution. Then we have the interquartile range. Quartiles are indicated for a distribution of scores. The middle 50% of the distribution consists of those scores between the first and third quartiles, Q1 and Q3. Quartiles are indicated for distribution of scores. Again, the middle 50% of the distribution consists of these scores between the first and third quartiles, quartile 1 and quartile 3. The most common and most important measure of variability is standard deviation. This is a measure of the standard or average distance from the mean. So the way you can think about these are traditional IQ scores. So everybody's about 100 if you're average intelligence. And if you're 15 deviation points, like 85, you can do less cognitively. If you're a 115, a 130, 145, you can do more cognitively. And it matters in deviation scores with intelligence because it represents what the deviation is and where the difference between what folks can do cognitively or not do cognitively. So this describes whether the scores are clustered closely around the mean or widely scattered. Calculation differs for population and samples. Variance is a necessary companion concept to standard deviation, but not the same concept. Variance is how scores vary. Standard deviation is a little bit more about clustering. It's the square root of variance. So we'll talk about that a little bit more. So step 1, determine the deviation. Deviation is the distance from the mean. The deviation score is X minus the mean. Step 2, find the sum of the deviations to use as a basis for finding an average deviation. So 2 problems, deviation sum to 0 because mean is the balance point. If the sum is always 0, the mean deviation will always be 0, which means you need a new strategy. So step 3, remove negative deviations. First square each deviation score, then sum the square deviations, sum of the squares, average the square deviations. The mean square deviation is known as variance. Variability is now measured in squared units. Variance equals the distance mean average of the square deviation's distance minus the average distance squared for the mean. So we have some worksheets where we walk through that a little bit, and we'll walk through it as we continue here with the course. Defining variance and standard deviation. Variance, the step 4 goal to compute a measure of the standard average distance or the scores from the mean. Variance measures the average square distance from the mean, not quite our goal. We want to adjust by squaring each distance, find the average of the square distances, and take the square root of the variance. Standard deviation is equal to the square root of variance. So calculating variance and standard deviation, find the deviation, distance from the mean, square each deviation, find the average of the square deviations called variance, take the square root of the variance, and then the standard deviation or standard distance from the mean. So we have our standard deviation in terms of how the score, this is a histogram. The mean for the population is 6, smallest distance from the mean is 1 point. The largest distance is 5 points. The standard distance or standard deviation should be between 1 and 5 points. So variance is the sum of the square deviations over the number of scores, like what I showed you with Excel. The sum of the squares is the sum of the square deviations, squares from the mean. And that there's two formulas. So the sum of the squares, the definitional formula, find each deviation score, square each deviation score, sum of the square deviations. The computational formula, square each score, sum of the squared, and the sum of the squared scores, find the sum of the scores, square it, divide it by n or your population, subtract the second part from the first, like this. So what I think you could just remember to keep this just a little bit more simple, everybody, would be following. Just remember this for now. The sum of squares. Sum of the squares over n, that is your variance, okay? What I showed you, you take all the values, you square them, divide them by n, total number of things happening, okay, for your population. Then for your standard deviation, just remember this. This will be just a little bit easier than I think the way the book is telling us. Square root of the sum of the squares over n, standard deviation, okay? Literally that easy. Sum of the squares over n, square root of the sum of the squares over n, okay? I think that's a much easier way to think about the concept. So let's stop our share. Let's go back to our chapter here. Sure. I believe we were right here. So for that, maybe that'll just a little bit more clear. And just remember my formula, I think. Some final formulas and notation for population variance, population standard deviation, literally what I just said. Remember these formulas right here. That's a little bit easier. Variance is the average of the square deviations. So we identify the population variance with lowercase Greek letter sigma squared, like that, theta squared. Standard deviation is the square root of the variance. So we identify with the lowercase Greek letter sigma, like that, theta, just by itself. So decide if these are true or false. The computational and definition formulas for the sum of the squares sometimes give different results. True or false if all the scores in the data set are the same and standard deviation is equal to 1. Both are false. The computational formula is an algebraic rearrangement of the definitional formula. Results are identical. And false, when all scores are the same, they're equal to the mean, their deviations are 0, as is their standard deviation. The standard deviation measures what? A sum of the deviation scores, a standard distance of a score from the mean, an average deviation of a score from the mean, or an average square distance of a score from the mean. And that is the standard deviation measures the standard distance of a score from the mean. So some goals of inferential statistics. Draw general conclusions about the population based on limited information from a sample. Samples differ from the population. Samples have less variability. Computing the variance and standard deviation in the same way as for a population would give a biased estimate of the population values. So this is the population of adult height forms a normal distribution. If you select a sample from this population, you are most likely to obtain individuals who are near average in height. As a result, the variability for the scores in the sample is smaller, less spread out than the variability in the scores for the population. So then we have the sum of the squares, which is computed as before. The formula for variance has n-1 rather than n in the denominator. So variance of the samples, sum of the squares over n-1, or standard deviation. Again, the same formula. Remember, n-1 in a sample, That's the small n, the smaller group of the larger population. N by itself when you use the population. So here's your variance of the sample, sum of the squares, n divided by n over 1, or the square root of the sum of the squares divided by n minus 1, and n is the number of items or things you have, remember. So this is the frequency distribution histogram for a sample of n equals 8 scores. So remember, population variance, the mean is known. Deviations are computed from a known mean. Sample variance is an estimate of population. Population is unknown. Using the sample mean restricts variability. Degrees of freedom, number of scores in the sample that are independent and free to vary. Degrees of freedom for a sample equals n minus 1. A sample of 4 scores has the sum of the squares of 24. What is the variance? A sample of 4 scores is 24. What is the variance? What do you think? It's 8. How do we know? Sample of 4 scores, sum of the squares is 24. So 4 divided into 8 is 24. That's how we got there. All right, true or false? A sample systematically has less variability than a population. The standard deviation is the distance from the mean to the farthest point on the distribution curve. What do you guys think about that? So true, extreme scores affect variability, but are less likely to be included in a sample. False, the standard deviation extends from the mean approximately halfway to the most extreme score. So sample variance is an unbiased statistic. An unbiased estimate of the population parameter. Average value of a statistic is equal to the population parameter. Average value uses all possible samples for a particular sample size, n. The corrected standard deviation formula dividing by n minus 1 produces an unbiased estimate of the population variance. A biased estimate of a population parameter systematically overestimates or underestimates the population parameter. So this table illustrates with the known population that both the sample mean formula corrected and the sample variance formula produced unbiased estimates of their corresponding population parameter. So I'll show you something in a moment that'll make this make a little more sense in terms of grabbing a sample out of the mean, their unbiased sample mean or biased sample mean. So we'll walk through that a little bit more. So more about variance and standard deviation. Means and standard deviations are particularly useful in clarifying graphs or distributions. Means and standard deviations together provide extremely useful descriptive statistics for characterizing distributions. So for both populations and samples, it is easy to represent the mean and the standard deviation. The vertical line in the center denotes the location of the mean, and the horizontal line to the right, left for both denotes one distance of standard deviation. So this is showing a mean and standard deviation. A population distribution with a mean of 80 and a standard deviation of 8. A sample with a mean of 16 and a standard deviation of 2 for this right here. So some transformations of scale, adding a constant to each score, the mean is changed, the standard deviation is unchanged. Multiplying each score by a constant, the mean is changed, the standard deviation is also changed, the standard deviation is multiplied by that constant. Standard deviation and descriptive statistics. A standard deviation describes scores in terms of distance from the mean. Describe an entire distribution with just 2 numbers, the mean and the standard deviation. Reference to both allows reconstruction of the measurement scale from just these 2 numbers. A sample of n equals 20 and a mean of 36 and a standard deviation of 4. So the goal of inferential statistics is to detect meaningful and significant patterns in research results. Variability in the data influences how easy it is to see patterns. High variability obscures patterns that would be visible in low variability samples. Variability is often classified as error variance in the context of inferential statistics. The sample variance represents unexplained and uncontrolled differences between scores. Figure 4.212, graphs showing the results from two experiments. Experiment A, the variability is small, and it's easy to see the 5-point mean difference between the two treatments. In experiment B, however, the 5-point mean difference between treatments is obscured by the large variability. All right, learning check. A population has a mean of 6 and a standard deviation of 2. Each score is multiplied by 10. What is the shape of the resulting distribution? Is the mean 60 and the standard deviation 2? Is the mean 6 and the standard deviation 20? Is the mean 60 and the standard deviation 20? Is the mean 6 and the standard deviation 5? Well, the answer is the mean is 60 and the standard deviation is 20. So true or false? A biased statistic has been influenced by researcher error. True or false? On average, an unbiased sample statistic has the same value as the population parameter. False, bias refers to the systematic effect of using sample data to estimate a population parameter. True, each sample statistic differs from the population parameter, but the average of all samples will equal the parameter. And this is what it would look like with SPSS. We are going to work with SPSS. There's actually some things posted on how to do stuff with SPSS. There are SPSS assignments coming, and we will walk through that. In fact, I might do a little bit of that tonight. If you have questions, do please ask. Show. All right, let's look at a few more things in SPSS. So here we go. This is SPSS, and let's code some variables. Let's say that this is how much sleep you get, and let's say that this is how much you study. And let's make these decimals 0. And then let's do some data. So more data. Just making up these numbers as we go. All right, so what we can do is we will analyze reports, descriptive statistics, frequencies, and then move these over here. We'll just start with one just for simplicity's sake. Click sleep statistics, and you can ask for the mean, the median, the mode, quartiles, standard deviation, variance range, minimum, maximum. Continue. Call it okay. Now, give it just a second, get an awesome file like this, and it tells you all of those things. Literally that easy. Look how awesome statistic SPSS is. Mean, median, mode, standard deviation. The 2A tells you there's multiple modes. The smallest mode it shows you. Standard deviation, variance, range, minimum, maximum. So that's, I think, pretty awesome. You can also some of the stuff in Excel. I'll probably post some stuff for you guys in that too, so you can play around in Excel as well on that. So one more thing I'll show you just a moment. All right, and one more thing to conclude this lecture. This, I think, is rather awesome. So we have the dance of the means. So we have any population, we'll say 50. We'll say we have standard deviation of 20. Now, watch what happens when I take a sample. You see the green circles? That is showing when you take a sample of the population, your mean of your sample tends to reflect the population. Now, as you can see, it stays pretty close to the mean. Now, part of the reason that it differs a little bit is that standard deviation. So if we move this, make this a little smaller, let's say 11, and start again, as you can see, we're taking a sample of the population mean, but look, the mean stays of the sample stays very, very close to the population mean. So the green is the sample mean from the population. And as you can see, as we do this heap here, it stays very, very close. So the sample mean is generally pretty close to the population mean. And of course, it's going to vary more if we have a larger standard deviation. See, now it's going to be a little further away because our standard deviation. But as you saw before, when that's a smaller, it's real small, standard deviation, do that again. Look how close that sample mean stays to that population mean. Population mean, again, is that blue line, and those green circles are sample means from the population. So that concludes our lecture. I hope that resource was helpful. I look forward to hopefully seeing everybody in a regular live class. I need to hear from you all. I'll probably call people tomorrow to try to get a sense of the best time to meet you. I've been expecting some emails, and a few of you said you would get back to me. I think it's just the 3 of us, myself and 2 other people. So I think scheduling a time should be pretty easy. Hope you enjoyed the lecture. Hope to see you all in a live lecture real soon. Hopefully we can coordinate something tomorrow on the 21st of October. My number is 786-879-0179. Call me, text me, email me, jkmack@ferrum.edu. Hope to find a time that works for everybody. Take care, and I hope to see you all in class real soon.